Hello and welcome to lesson 1.4. Today we're going to look at perimeter and area in the coordinate plane. Recall that a figure that lies in a plane is what we call a plane figure, and a polygon is a closed plane figure formed by 3 or more line segments, which we call the sides. Each side is going to intersect in exactly 2 sides, and these are going to intersect at what we call the vertex. So no 2 sides with a common vertex are going to be collinear. So as you can see here, when I have 2 side lengths, so in this case I have side CD and side ED, these 2 sides are going to intersect at what we call vertex D. Just like side AE is going to intersect side AB at vertex A. Now when we name polygons, polygons are named by their vertices, okay, which is the plural word for a vertex. So in this case, I have polygon A, B, C, D, E, and that's how we would name this figure here. Some common names for polygons are listed here. You can see that a 3-sided polygon is a triangle. A 4-sided polygon is what we call a quadrilateral. 5-sided polygon is a pentagon. Then 6 sides means we have a hexagon. 7 is a heptagon. 8 is an octagon. 9 is a nonagon. 10 is a decagon. 12 is a dodecagon. And then n, like meaning any number bigger than 12. So if it was 15, it would just be called a 15gon. When looking at polygons, we can classify polygons in one of 2 ways. They're either known as being a convex polygon or a concave polygon. A convex polygon occurs when no line contains a side of the polygon that contains a point on the interior of the polygon. So if you notice, there's no, like if I draw a line on any one of these sides, it doesn't cross over the inside of that polygon. So again, that's convex. A concave polygon is a polygon that's essentially not convex, meaning that if you draw a line on one of your polygon sides, it will actually go through, and you can see that it goes through right in here, but it will actually go through at least one part of that polygon. So when we look at example 1, it wants us to classify each polygon by the number of sides and tell whether or not it's convex or concave. So when you look at part A here, we can see that we have 1, 2, 3, 4 sides. So it's 4 sides, which means that we really have a quadrilateral, okay? And because my polygon has a side, and it only takes 1, where if I follow that side length, I can actually cross through another point, or the inside of my polygon at some point, then that means I have what we call a concave polygon. So this here would be concave. Meanwhile, for part B, we have a 1, 2, 3, 4, 5, 6-sided polygon. A 6-sided polygon is actually what we call a hexagon. And when I try to draw lines along the sides, I can see that I'm not going to cross through the interior at any point. Therefore, this is a convex polygon. Please pause the video and take a second to try to answer these on your own, and then come back and double check your answer. So for number 1 here, we have a 5-sided pentagon. And if I can draw a line on one of the sides that goes to the interior of that, that means that I actually have a concave polygon. So this is concave. Likewise, for number 2, I can see that I have 1, 2, 3, 4, 5, 6, 7. So 7 sides means I have a heptagon. And if I try to draw lines on any of the edges, they're all going to be on the outside, which is going to make this convex. Finally, for number 3, we have a 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 sides, which is what we call an octagon. And because I can't draw a line that's going to go on the inside of that polygon, that means that I have, again, another convex polygon. Now for number 4, it says, can you draw a concave triangle? Okay, and on this polygon, you cannot, because there's no way that you can draw a shape. If you think about a triangle, and it doesn't matter how you draw it, you can't draw your triangle where you trace one of the sides and it's going to go on the inside of that triangle. So the answer for number 4 would then be no. Now this slide here is just kind of a review. Hopefully you've seen some of these formulas before for perimeter and area of some common polygons. We have triangle. Remember, perimeter is when you add up the lengths of the outsides. So notice it doesn't matter if you're doing a triangle, a square, a rectangle, or a parallelogram. You are literally just adding up all the side lengths. Now for area on a triangle, it's 1/2 base height. On a square, we're going to take and multiply your length times your width, or in this case, because square side lengths are all the same, it's times width. And then your parallelogram area, they call it base times height. So it would be the base, and the base is defined as the side that is perpendicular to the height of that parallelogram. So let's go ahead and look at example 2 and see how we're going to use these. So example 2 says, find the perimeter of triangle DEF with vertices at 1, 3, 4, -3, and -4, -3. So the first thing we have to do is we have to plot these points. Now that I have my points plotted, I have to find the side length of each side so that I can go ahead and add those up to find the perimeter. Now to do this, we're going to have to treat each side length as its own piece, and we're going to have to apply the distance formula. If you remember, the distance formula is the square root of the quantity of x2 minus x1 squared plus the quantity of y2 minus y1 squared. And I would suggest that you label your points x1, y1, x2, y2, because sometimes things can get a little bit tricky and confusing. So if you have things labeled, it just makes things go a little bit better. So you can see I've gone ahead and labeled point D as my x1, y1, and E as my x2, y2. So now all I have to do is plug in my points. So for segment DE, I'm going to take the square root of my x2 is going to be 4 minus my x1, which is 1, and I'm going to square that and add that to my y2 value, which is -3, minus my y1, which is also 3, and we're going to square that. So when I simplify all this, 4 minus 3 will give me 3 squared, and then -3 minus 3 is really a -6, and I'm going to square that. 3 squared is 9. A -6 squared will give me a positive 36. And when I add those two together, I really get the square root of 45. And if you want to punch it in your calculator, you can see that that's about 6.71. So for now, I'm just going to write that DE is the square root of 45. And then we're going to have to go and find the side length of another side. So I'm going to go ahead and look at FE, because FE is a nice horizontal line, and I can see that that is 8 units long as we're going from -4 to a +4. So this here is going to be 8. And then the last side length I have to find is FD. So I'm going to just go ahead and call x1, y1 on point F and x2, y2 on point D, since it's already labeled. So now for segment FD, I have the square root of x2 is 1 minus a -4, and we're going to square that and add that to the difference of 3 minus a -3, and we're going to square that. So when I simplify, 1 minus a negative really becomes 1 plus, or 5 squared, plus 3 minus a negative really becomes 3 plus 6 squared. So this is going to give me 25 plus 36, or the square root of 61, which is approximately equal to 7.81. So now, because we had to find the perimeter, we really need to add all of these up. So I really have the square root of 45 plus 8 plus the square root of 61. So we said the square root of 45 was approximately 6.71 plus 8 plus the square root of 61, which is roughly 7.81. So if I add all these together, this is going to give me something around 22.52, and I'm just going to put units for now because perimeter is really a length and I wasn't given a unit, so I'm just going to put units. Please let me know if you have any questions. Otherwise, I hope you guys have a great day, and I'll see you in class tomorrow.